Now, the problem that we are trying to solve is we have a robot arm, and this robot arm, we actually used the Lagrangian equation and other different techniques and came up with the differential equation of motion. And now what we want to do is somehow we want to solve these differential equations of motion. So we want to solve differential equation of motion. So clearly one technique is using MATLAB, because the differential equations that we study are typically ordinary differential equations. Another equation, way you can solve these differential equations of motion is using Laplace transform. Laplace transform can only be used to solve linear differential equation with constant coefficients. So what are we trying to do here? If you look at the robot arm, this robot arm comes up with a very big differential equation, which is something like mx double dot plus kx plus cx dot is equal to f of t, this type of an equation. And what we want to do is we want to find out whether this differential equation is stable or unstable. Which means if we were to give a robot arm a perturbation, so if I were to give a small perturbation, whether the robot would come back to its original position or would it drift. So this example is very commonly given when we talk about the stability. Is if you think about it, you can have some type of a disc or a sphere in a bowl. This will actually go back and forth, and finally settle down to the equilibrium position. When that happens, this is asymptotically stable system. Imagine the same sphere on the horizontal surface. This is simply stable. Or this bowl could be upside down, inverted, and the system would be unstable. So same thing happens with the robot arm. So we want to understand if the robot arm that we are designing or we are studying is stable or unstable. And if the robot arm is unstable, if robot is unstable, we want to add a controller to control it. So what that means is there are two types of motion control systems. One is an open loop system, when what we have is we have this system, or it is also called as plant. you provide an input to the plant, and then you have the output. A simple example is if you look at the 3D printers, they have something called as the stepper motor. So you provide an input to the stepper motor and stepper motor moves. So in the case of open loop system, you have an input. That input is acted upon by the plant and the output comes out of the plant. In the case of closed loop system, you have input and then you have the plant. You have the output. What happens is this output is sampled back and you have this input, and here what you have is you have the error. So what that means is there is a feedback. So this is the feedback. And that's why this system is called as the closed loop system. Typically, the robots, they operate in closed loop. Now, there are many robots. If the robot is used for a very simple application, typically we use stepper motors. But if the robot is used for mission critical complex operations, then a servo motor is used. For stepper motors, typically they run in open loop. The closed loop systems typically have some type of a feedback, either an encoder or a resolver, or maybe some other type of sensor that makes sure the system is running in closed loop. Now, all this system, as you can see, there are different ways of designing an open loop and closed loop system. And as we talked about, we have this complex dynamical system, which is actually a nonlinear system, higher order system. And what we do is we somehow simplify this, some simplification process. And after we simplify, we get this linear model. And once we have a linear model, this linear model, we can use some linear control techniques to control this linear system. Now, please try to understand this linear system is valid in the limited range. I give you an example. Imagine if you have a sine function. If you use the approximation sine theta is equal to theta, this approximation is valid only in the limited range. Because if you exceed this operating range, then the system will no longer behave like a linear system. And you need to understand the operating region for that particular system. So you have to be very careful when you are using this linear approximation. This linear approximation should be in the domain or region or region of operation. So the question is, what is a easier way to control this type of a system? And in the past, what we have seen is, if you want to analyze, we can use uh, the Laplace transform. Probably you have seen this, or you can use some type of approximation techniques. You can use closed form solution, or you can use numerical integration that we used in the case of our previous assignment. So in today's class, what we are going to do is we are going to look at something called as a concept known as the transfer function. So transfer function by definition is given as the Laplace transform of output divided by Laplace transform of input. So transfer function is nothing but Laplace transform of output divided by Laplace transform of input. And most of you might have seen this concept of Laplace transform, but for my own satisfaction, I'm going to give you a quick overview of what Laplace transform is. Now, Laplace transform is a simplification technique, and this technique is somewhat similar to logarithms. So, I want you to understand the logarithms were invented because we wanted to multiply these two big numbers, and it was not possible to perform this big multiplication using the available resources in the time that is needed. So you have a large number here, you have another large number here, and then this multiplication is going to be very, very large. So with logarithm, what we did, once we take the log of this function, then I get a small function, a small value. When I take the log of this, I get a small value. And these two small values of multiplication in the actual domain is addition in the log domain. So what that means is basically you can add these numbers and then find out the antilog, and you got your answer. So what happened? This process of multiplying two huge numbers is eliminated, and we convert this into summation of two small numbers. Now similarly, when we use the Laplace transform, what happens is we have this differential equation. This differential equation is x dot plus x is equal to 0. We use the Laplace transform, and this equation becomes an algebraic equation. And then once you do the inverse Laplace, you get your solution. Now what that means is you are eliminating, there is no integration. So what does Laplace transform do is Laplace transform takes a differential equation. So it takes a differential equation and converts that into algebraic equation. So what logarithm does to multiplication, Laplace transform does to differential equation. Now, one thing I want you to understand that Laplace transform can be used for linear technique. I mean linear differential equations. And I'm not gonna give you the theory of Laplace transform, but what I'm gonna do is I'm gonna talk about how to convert systems into a Laplace transform. So basically, if you think about it, this is the time domain. And here is the Laplace domain. In time domain, independent variable is t. In Laplace domain, independent variable is x. In time domain, it is x of t. In the Laplace domain, it is going to be x of s. In time domain, the input is u of t, and in the Laplace domain, it is going to be u of s. And if you have x dot d by dt of x of t, x dot, in Laplace domain, this become s of xs. So whenever you have a dot, that get replaced by s. So now if you have x double dot in the Laplace domain, this is going to be s square x of s. If you are going to integrate, this is going to be 1 over s. So let me take a simple example. So example, so if I have a differential equation x double dot plus x is equal to u of t. And this is the differential equation in time domain. And I would like to convert this into the Laplace domain. So what I would do is, first, I would actually convert this something like s square x of s plus x of s is equal to u of s. Now, what is the input and what is the output? This is the input because this is the forcing function. And this is the output. So what we do is this x of s comes out s square plus 1 is equal to u of s. And this is the equation in Laplace domain. So now if I want to represent this equation as a transfer function, then what I do is transfer function is given as Laplace transform of output divided by Laplace transform of input. So as you can see, output is x of s, input is u of s, the transfer function is going to be 1 over s square plus 1. So if I have this differential equation, And if I want to write this as a transfer function, the open loop transfer function is given as 1 divided by s square plus 1. Input. So input is going to be u of s, output is going to be x of s. Now, this transfer function has a numerator, so I'm going to write this down. Transfer function has a numerator and a denominator. Typically, numerator is function of s, denominator is function of s. So in this particular numerator, there is only a constant 1, but in most general case, you will have some type of function that is a function of s, and you will have some type of function that is in the denominator that is function of s. So for certain values of s, if the denominator of s is equal to 0 for certain values of s, these values of s are called as the poles of the transfer function. So means, when does the numerator or denominator becomes 0? So what are the values when the denominator becomes 0? So in this particular case, I want you to see the denominator is s square plus 1. So s square plus 1 is equal to 0. So s is equal to plus minus square root of minus 1. So s is equal to plus minus I. So when s is equal to plus I or s is equal to minus I, we are going to get the denominator of this transfer function that will be equal to 0. In certain cases, the numerator can be function of s, could be 0. In this particular case, it is not possible, but for certain values of s, these are called as zeros. So let me take an example here real quick. So now my output, so example, my output
70 to 61.
is velocity. Okay, input is forcing. So my output is x dot, my forcing is u of t. So if you look at my transfer function, the transfer function, which is output divided by input, is going to look like s divided by s square plus 1. Because please understand, we have x of s, which is x of t. If I want x dot, then I need to multiply by s multiplied by x of s. So my transfer function is this. So here, now I have a numerator that is function of s. So zeros is equal to s is equal to 0 is the 0 of transfer function. This transfer function does not have zeros. So transfer function are very important and that are used in lot of applications. So let's quickly take a look at how we can use this transfer function approach for control system analysis. So a robot would have certain transfer function. And if it's an open loop transfer function, it will be input. You will have a transfer function, output. Now let's look at what happens if you have a closed loop transfer function. In closed loop transfer function, you are gonna have an input. That input gets compared with an output, and the output, the difference between the input and the output, which is called as the error, is fed back to the transfer function. So I'm gonna call this HS, and this is, so I'm gonna call this U. I'm gonna call this, say, Y. This is U of T. This is Y of T. And typically the transfer function is denoted as G of S. And what you have is you have a feedback here, which is H of S. So this is the transfer function of feedback. Now, what does this transfer function of feedback means? Say transfer function of feedback means, it's, say you have a car. Okay, you have a car. And you want to measure the distance traveled. Unfortunately, you cannot measure the distance traveled by car directly unless you have these mile markers. So you know this is mile 1, and maybe this is mile 2. And once you actually cross this mile 1 and mile 2 mile markers, you know that we traveled 1 mile. But if you don't have a GPS or some type of any other independent measurement, this mile markers may not be known, so the displacement may not be known. But what you can know is, you know the speed of the car or the velocity of the car. So what you have is, you have the feedback not directly on the displacement, but actually you have the feedback that is on the velocity. So if I wanted to write down the transfer function of this car, think about it something like this. So this transfer function of the car is given as, say, x double dot is equal to some type of an acceleration. And then what we do is, we take this into the transfer function model. And since we know the transfer function of the feedback, and our feedback is in the form of velocity feedback, we will have some h of s that is indicating the velocity feedback. Many a times you just sample the output. So imagine, instead of the speed, what you have is, you have the GPS measurements. If you have GPS, then directly you have the travel distance, how far that we have traveled. And once we know this, the distance that is traveled, then we have the direct measurement of the feedback. And that could look like something like UT, then input, you have transfer function, you have the output, and then you just have no one unity feedback. So this is unity feedback. So let's try to derive the closed loop transfer function. So what I'm going to do is I'm going to take this particular transfer function, which I showed over here, closed loop transfer function, and then I'm going to derive the transfer function of the closed loop system. So think about it like I'm going to combine this whole thing into one transfer function. So u of t is coming in. Then here you get y of t, y of s. Y of s gets multiplied. So you have u of s plus minus h of s, y of s, that gets multiplied by the transfer function g of s, that gives you y of s. So expand this, it will become u of s, g of s minus h of s, y of s, g of s is equal to y of s. Now we need to take terms together. So as you can see, these y terms should go together. So u of s, g of s is equal to 1 plus h of s, g of s, y of s. And then when I say y of s divided by u of s is equal to 1 plus h of s, g of s. So this is called as the closed loop transfer function. Now what happens is, if you have a feedback, then as you can see, because of the feedback, the poles and the zeros of the transfer function are modified. Now this transfer function approach is extremely important when we are trying to perform something called as the system analysis. And when you look at the system analysis, is nothing but response of system to input. And when we talk about the response of the system, there is something called as the transient response. And then there is something called as the steady state response. So transient response is the initial response, and the steady state response is sort of the long-term response. So if you look at what we are trying to understand, is I give you a simple example, is imagine that if you have a spring mass system, and if you perturb this system, then what's going to happen is this system is going to oscillate back and forth. But imagine if you add a damper to this system, what's going to happen is this system response is sort of going to die down. Now let's understand that you have a stiffness, you have a damper, you have a mass, and then on top of it, you're applying some type of a forcing excitation, say U of t. So what would happen is because of this external forcing, and this could be a periodic forcing, sine t, you would realize that initially this would be like going up and down. It will, and then it will continue to oscillate at the frequency of external forcing function. So please try to understand, transient response is due to initial conditions, and steady state response is due to input. Now, if you are looking at the linear system, the important part of the linear system response is something called as the magnitude and phase. So let me show you what that means. Say if you have a linear system, which means you have a transfer function, and there is some input to this transfer function, and then there is some output. You can find out the ratio of output divided by input. This is called as the magnitude. So whether output is greater than input or output is of same order of magnitude as the input. Or you can also see whether the output is leading or lagging. You can also check if the output is leading or lagging the input. So this is what we mean by phase. So a linear system can be very well characterized by its magnitude, and it can be characterized by its phase. So magnitude is a ratio of output divided by input, and phase is whether the output is leading or lagging. Now, to understand this system behavior, we can actually construct a transfer function and perform some type of analysis, and that analysis allows us to dictate or to understand whether the system is stable or unstable. We talked about different types of stabilities. We talked about the asymptotic stability. We talked about the simple stability, and we talked about instability. There is another important concept that is considered in linear system, which is called as the bounded input. Bounded output stability. So which means if your input is bounded, if your output is bounded, that is called as bounded input, bounded output stability. What that means is system will not blow up in operation. So that is called as bounded input, bounded output stability. Now there are multiple types of systems, and one important aspect that we need to take into account is the order of the system. So system order. So system order is nothing but the highest order of derivative in that system dynamics. So for an example, if we have a system 4x 5, which is the zero order system, because no derivative term. Then you can have 4x dot is equal to 5. This is the first order system, because the highest derivative is dx by dt. And if you have 4x double dot is equal to 5, this is called as the second order system. So what are the characteristics of the zeroth order system? Zeroth order system is very quick, which means if you apply the input, you would suddenly get an output. A very simple example of the zeroth order system is nothing but a spring. The first order system is there is some type of a delay, and so spring is an example of the zeroth order system. So if you look at the thermometer, is the first order system, and second order system is nothing but a spring mass system is the second order system. So when we try to understand the behavior of the system, there are some important concepts that we need to take into account. Say, first and foremost, there is this concept which is called as the DC gain. So let's consider first order system. So first order system means the system will have only one derivative. So y dot is equal to ay is equal to bu. Now this equation can be written as 1 divided by a y dot plus y is equal to b by a u. Now what I'm going to do is I'm going to convert this equation into the Laplace domain. U is the input, y is the output. So this equation will become 1 divided by a s y of s plus y of s is equal to b by a u of s. Because please try to understand, y dot of s is equal to y dot of t is S, y of S, y of t is equal to y of S, u of t in Laplace domain is u of S. So this becomes like this. So 1 divided by a S plus 1 y of S is equal to b by a u of S. So this transfer function can be written as y of S u of S is equal to b by a divided by 1 by a S plus 1. So this becomes b by a is called as DC gain, and 1 by a is called as tau or time constant. So what is the definition of DC gain? Is the ratio of magnitude of steady state response to step input, and time constant is the amount of time the system takes to reach 63% of steady state response. So DC gain is kind of ratio of output divided by input, and the time constant is the amount of time it takes to reach the 63% of the input of the steady state response. Then there is another concept which is called as the settling time. Settling time is the amount of the system takes to fall within certain percentage of output. So for an example, you can think about a 10% settling time, 5% settling time, 2% settling time. So depending upon what characteristics you are trying to study, there could be 10% settling time, 5% settling time, or 2% settling time. There is another concept which is called as the rise time. Rise time is amount of time needed by system to reach certain percentage of steady state value. So for an example, sometimes you try to find 90% rise time, so which means the amount of time it takes to reach 90% of the steady state value. So please understand, settling time is the percentage within the output, and the rise time is percentage to reach that certain percentage of the output. So it's actually very important that we understand these concepts, because if our robot is having some type of a time constant, which means that is the amount of delay that we have to account for, or we have to compensate for, or be ready to uh, somehow incorporate in our application. If the robot is a first order system, then there will be some time constant, there will be some rise time, there will be some delay. If the robot is the zeroth order system, then the response will be immediate. Otherwise, it will take some time for the system to get to certain percentage of signal value. Now, let's a very simple example. Let me consider a simple example. If you have a spring mass damper system, for the spring mass damper system, so this system is given by something like this. And there is an external forcing F of t. So the differential equation of motion is given as my double dot plus cy dot plus ky is equal to f of t. And as we know, this m is the mass, this is the damping, this is the stiffness, and this is the forcing. So if I want to find out the transfer function of this system, then I can convert this differential equation into m s y of s plus c s y of s plus k y of s is equal to f of s. Please understand, since there are it's a double derivative, so that's why I have this s square. Since there is just single derivative, I just have s, and there is no derivative, so y of t is y of s. Now I take this out. Y of s is equal to f of s, and then I have the transfer function, which is the Laplace transform of output divided by Laplace transform of input, which is y of s divided by f of s is 1 s square cf plus k. And this is the transfer function of this system. Now this system could be stable or could be unstable. So a classic way of controlling the system is by means of something called as the PID control. So PID control is proportional, integral, derivative control. So what happens is we add a controller term to control the dynamics that is proportional to error. We add a controller term which is dependent on the integral of error, and we add a controller term which is dependent on the derivative of error. So what that means is, say you have a system dynamics. So I'm going to give you an example. Say mx double dot plus cx dot plus kx. And I want to add a controller term to it. So I'm going to add this k hat term to it. This is kind of a controller term. And this control will be dependent on the error or the difference between the output and input, and that this controller term could be proportional to the error, it could be dependent on the integral of error, or it could be dependent on the derivative of error. So just to give an example, consider that we have the transfer function is input, there is an output coming in here. So here we have error. This error gets fed to a controller term, and this whole thing gets fed to the transfer function, and then what you have is you have an output. And I'm going to assume a unity feedback. So this controller term that we talked about, PID control, can be over here. So if I want to write down the expression, controller could be Kp, which is the constant of proportionality, multiplied by this error, which is E of S. So I would write this in the time domain, and then we will do it in the controller, in the frequency domain or Laplace domain. E of t plus ki proportional, this is integral, E of t dt plus kd E dot of t. So this is, as you can see, this is proportional, this is integral, and this is derivative. So PID is a nice way of controlling the system dynamics, and commonly used in industry. If we want to express this PID control in terms of transfer function, this will become Kp plus integral term Ki by S plus Kd times S multiplied by, as you can see, E of t will come common outside, E of S. So E of S is called as the tracking error, and Kp is called as the proportionality gain. Ki stands for the integral gain, and Kd stands for the differential gain. So in today's class, what we looked at is we looked at the basic concept of motion control system. Now here is the big picture of the motion control system. We have a robot, we use Lagrangian approach and came up with this differential equation of motion. Now these motions are nonlinear, but if we were to linearize it or somehow approximate these equations, sometimes like a linear equation, then we can use Laplace transform techniques to solve this problem. When we talk about the stability, we want to understand if the robot is stable on its own, or we want to add some external controller to stabilize the robot. And depending upon the system dynamics, the robot could be asymptotically stable, robot could be simply stable, or the robot could be unstable. So asymptotically stable means even if you disturb the position of the robot will go back to its original position. Simply stable means if you disturb the robot would assume a new position. Unstable means if you disturb the robot, then the robot will never gonna go back to its original position. The other thing that we want to consider if the robot has bounded input, bounded output stability, which is called BIBO, P-I-B-O, which means if the input, the disturbance on the robot is bounded, whether the robot output is going to stay bounded or not. Just to make sure that the system or the robot doesn't behave abnormally or doesn't go out of bounds when the robot is disturbed from its operating position. You can actually look at the system behavior as an open loop system. You have some input, you have a plant, and you have an output. You can add some type of feedback and convert that system into closed loop. So what you have is you have an input, you find out the difference between the output and the input, and that constitutes the error, and then you feed that error to the plant, or somehow you use a controller. Now, transfer function is another approach where we look at this can be used for analysis of linear systems. For an example, if your robot is a linear system, then you can construct the transfer function for the robot, which is nothing but the Laplace transform of output divided by the Laplace transform of input. So Laplace transform is a technique that converts the differential equation into algebraic equation. So as I have shown here, if you want to convert the differential equation into an algebraic equation, you take the Laplace transform and then you can actually solve the system. So in time domain, the independent variable is t. In Laplace domain, independent variable is s. Time domain, dependent variable is x of t. In the Laplace domain, the dependent variable is x of s. Input in time domain is u of t. Input in time domain is u of s. If you have the derivative x dot in the Laplace domain, it becomes an algebraic expression s multiplied by x of s. If you have x double dot in Laplace domain, it becomes s square x of s, and the integration becomes 1 over s. And we looked at 1 over s block in Simulink when we tried to solve the Simulink code, the Simulink function that we obtained from the MATLAB. Now, when we have a transfer function, that is simply the Laplace transform of output divided by Laplace transform of input. In general, the numerator of the transfer function is dependent on s. It's a function of s. Denominator of the transfer function is a function of s, where s can take values from 0 to infinity. For some values of s, when the denominator is becoming 0, that is called as the poles of the transfer function. In cases when the numerator of the transfer function is becoming 0, that is called as the zeros of transfer function. Then we looked at the closed loop transfer function. So you have the transfer function of the plant, which is given as g of s. You have an input u of s, and you have an output y of s. And then once you perform the math that is shown over here, you get something called as the closed loop transfer function as shown on the right hand side. Now, when we look at the system analysis or the robot analysis, we want to understand the behavior of the system when there is some perturbation on some external change. There could be a transient response or transient behavior of the system. There could be a steady state behavior of the system. The transient response is dependent on the initial condition. The steady state response is dependent on the input. And for a linear system, you can look at either the ratio of output by input, which is the magnitude, and you can see whether the output is leading or lagging. That is called as the phase. And system can be analyzed using the magnitude versus phase type of analysis, which is called as the Bode plot. We also want to find out what happens as the gain of the system is changed. So if we change or tune the gains of the system, what happens to the behavior of the system? And that is achieved using something called as the root locus. Now the types of system, if there is no derivative, then it's a zeroth order system. 4x is equal to 5 is the zeroth order system. If there is one derivative, it's the first order system. If there are two derivatives, it becomes the second order system. Then for first order system, you have concept called as the time constant, you have the rise time, you have the settling time, and you can use these different types of analysis techniques or the system criteria to design the particular system. The last part of today's lesson is about adding the controller. A typical controller that is used for linear controls is the PID control, which is called as the proportional, integral, and derivative control. So we have a KP term, the term proportional to error. We have a KI term, that term is proportional to the integral of error, and we have a KD term, that is the term proportional to the derivative of the error. And in next class, we are going to spend some time on talking about PID. We'll spend time on looking how to find the root locus, and then we'll look at how to find the Bode plot. And with that, you should be able to solve the remaining assignments from the robotics 1 class. With that, I'm going to stop here, but I would be happy to answer any question you may have.